refrigerators now. Okay, so here's the idea behind refrigerators. Okay, so do you guys remember that to vaporize 1 gram of water, to convert that to vapor, it takes 540 calories per gram. Okay, so that's the latent heat of vaporization. And you have many liquids that have latent heats of vaporization. So coolants have latent heat of vaporization and stuff like that. All right, so the idea is the following. Let's say you want to cool the inside of this room or box or whatever. If you had a liquid, if you vaporize this liquid, you need heat. And so the heat would come from this environment. Okay, so this room would get cool. Okay, and that's the idea. So let's say what we do is, okay, now I'll just draw a little pipe. Oops, got into trouble there. Okay, so let's say this is a box you want to cool. And what we do is, okay, so you pass a coolant through it. And when the coolant is here, you vaporize the coolant. So it was a liquid coolant that was passing. And when it's inside here, you absorb heat from the inside and vaporize it. And now you're getting vapors. Okay, so when the liquid vaporized here, the coolant vaporized here, it absorbed heat. Okay, and you get vapors. And of course, outside here, you got to convert through a compressor, you got to convert it back to a liquid. And when you convert it back to a liquid, that releases heat. So you absorb heat from the inside and dumped it outside. Okay, and that's the idea of a refrigerator. Okay, so anytime you have to cool something, what you do is inside this tube, you have vaporized a coolant which absorbed heat from the inside. You brought that vapors outside in the compressor, you convert it back to liquid, which dumped the heat outside. Okay. And that's what this refrigerator did. So inside the refrigerator, so you have these coils. This is called the evaporator. The coolant evaporates here. And when the coolant evaporates, it absorbs heat. You come outside and, okay, so you absorb heat, you become vapors, you come back outside, and that goes through a compressor and becomes liquid again. All right, so it goes through a compressor, it's a high pressure vapor now. It loses heat because this vapor is hot and then becomes a liquid, so warm fluid. And then you send out the cold fluid again and it expands and vaporizes, it absorbs heat. So that's the idea. All right, so if you want to extract heat, what you do is you make a fluid, some kind of fluid. In this case, the coolant vaporizes, and when the coolant vaporizes, it absorbs heat. And that's how you take heat from the inside and dump it outside. So what you have done is you've taken heat from a colder environment and dumped it into a hotter, warmer environment. Of course, nature doesn't want to do that. There's a price to be paid, and you have to do work to do this. And the work is done in the compressor and all that. Okay, so that's how a refrigerator works. That's how an air conditioner works as well. Okay, an air conditioner is also taking heat from a colder environment and dumping it into a warmer environment. Okay. So refrigerators and heat pumps, they work the same way. So they take heat from a cold environment, and you have to do work to do that and dump it into the hot environment. So this is in joules, that's in joules. So let's say you do 2 joules of work and you're absorbing 5 joules of heat. What you end up dumping is 2 plus 5, 7 joules of heat in the hot environment. Okay. So ideal refrigerator. So the coefficient of performance of a refrigerator is defined as this. How much heat did you remove from the cold environment, and how much work did you have to do to remove that heat? So what we want is remove heat from the cold environment, and what we pay for is the work done. Okay, so QC by W. And for a Carnot refrigerator, the coefficient of performance is, again, this is QC, W is QH minus QC, and these are just, this ratio is just equal to the operating temperature. And again, these temperatures are on the Kelvin scale. So QC, the coefficient of performance is TC over TH minus TC, okay? Typical COP for a household refrigerator is about 5. So what that means is for every 5 joules of heat removed from inside your refrigerator, you're doing 1 joule of work. Okay, so that's what that means. Okay, a Stirling's engine is a more practical engine than a Carnot engine, but we won't talk about this. So this is a solar collector, a solar farm in Arizona that uses Stirling's engine. Okay. So it's focusing the sun's rays on the Stirling's engine, and that heat is converted to electricity. Okay. So a Stirling engine, a Carnot engine is 2 isotherms connected by adiabatic processes. In a Stirling engines, these are isochoric processes, and heat is exchanged in all 4 processes. But so the efficiency of an ideal Stirling engine is less than that of a Carnot engine. However, they have several advantages and they're being developed. Okay, so here's an Otto cycle. Here's what a real heat engine looks like. So car engine. A real heat engine based on Carnot cycle is not practical. The modern internal combustion engine uses an Otto cycle. So here's what happens. Here's the intake stroke. The intake stroke is when you're filling with air-fuel mixture. Then you compress the air-fuel mixture. And then when you light the air-fuel mixture, the pressure increases. Because of, again, this is on a PV diagram. And then the stroke, the working stroke, the piston expands and you're doing work. And then this is the exhaust, you're exhausting the used gases. And well, you open the valve when you exhaust the used gases. And then you intake more new gas and air fuel mixture, compress, light it, and then let the gases push the piston. Okay. So you saw that, and that's the cycle here. Okay. So there's the intake, compression. You lit that, expansion. Again, intake cycle, compression, light it. Okay. So there's the Otto cycle. All right, so there's the Otto cycle, and we are interested in the efficiency of this cycle. Again, these are adiabatic processes, these are isochoric processes, and so on. So this is different than a Carnot cycle. A Carnot cycle is isotherms and adiabatic processes. An Otto cycle is adiabatic processes and isochoric processes. All right, so this details all the steps. We talked about intake cycle, compression cycle, here's when the fuel is lit, here's when the fuel is lit, the pressure increases, and then the adiabatic expansion, okay, and then the exhaust cycle. All right, so the efficiency, this is the compression ratio. R is the compression ratio. The compression ratio is volume at when you took in air and a fuel mixture and compressed. V2 is the volume you compressed the air fuel mixture to. Okay, so V1 by V2 is that ratio. It's the compression ratio. And for most internal combustion engines, it's the compression ratio is between 8 and 12. The efficiency is given by, it's just related to the compression ratio, 1 minus R to the power 1 minus gamma. Gamma is the ratio of specific heats. And so you saw that for diatomic molecules, gamma is 1.4. And for more complex molecules, for the fuel, it's around 1.3. So anyway, this is roughly around 1.35 or so. Okay, so gamma is about that for an air fuel mixture. So the efficiency for an ideal Otto cycle would be 61.3%, 61.3%. Okay, with the compression ratio of 10.7. With a compression ratio of 9.5, that's the efficiency. So in principle, the IC, internal combustion, can be made more efficient by increasing the compression ratio, by increasing R. Okay. But the problem is, if the compression ratio is too high, the air fuel mixture will detonate before the compression is complete. That's called anti-knocking. Okay, and that's called knocking. And so you have all these anti-knocking tricks to prevent that. But anyway, that's the problem. So detonating before, premature detonating is a problem. So very high compression ratios also put stress on components. So for IC is the general compression ratio range is 8 to 10. Okay, so here are some of the problems with real auto engines. I'll let you guys read that. Okay. A diesel engine is more efficient than a internal combustion engine. Okay, so it's essentially the same. In a diesel engine, the difference is the following: you're only compressing air, so that premature detonation problem is solved. And then when you compress air, the air is hot, and then you inject diesel in. Then you inject the fuel. And the hot air, in the hot air, the diesel self-ignites. Okay? And then this is the power stroke. That's when the piston is pushed on and work is done. Okay? So air, introduce diesel, detonation happens to the power stroke. So the efficiency of so diesel engines do not compress a fuel air mixture, but rather air only. The fuel is introduced only after the air has been compressed, and the thermal energy of the compression ignites the mixture. Okay. So diesel engines have a higher compression ratio and thus a higher efficiency than gasoline-powered engines. And they have a slightly different thermodynamic cycle. And there's the efficiency of a diesel engine. This is the R is the compression ratio, and gamma again the ratio of specific heat. Alpha is V3 by V2. So alpha is V3 by V2. It's the volume after ignition to pre-ignition volume. Okay, so when the diesel burns, the gas expands, and that's an isobaric expansion. Okay, so that's the alpha. Anyway, diesel engines have higher efficiency than internal combustion engines. Okay. All right, so that ends that chapter. Again, let me briefly summarize this before we end the class. So what we saw was, we saw the second law of thermodynamics. We saw the second law of thermodynamics. And what second law of thermodynamics told you was heat flows from a hotter region to a colder region. And in nature, we never see this, okay? And that was because the second law states that only processes where entropy increases occur. Processes where entropy decreases do not occur. Then we saw heat engines. Heat engines convert heat to work, part of it to work. The efficiency of a heat engine is how much work did you get out of absorbing that much heat, okay? And E max is equal to 1 minus TC by pH, okay? Then we learned about refrigerators. We learned about refrigerators. And refrigerators, what they do is they remove heat from a cold reservoir and dump it into the hot reservoir. And of course, you have to do work to be able to do that. Nature does not want to do that on its own. Does not, okay? And so you were interested in such devices. And the coefficient of performance is defined as how much heat did you remove from the cold reservoir and how much work did you have to do for that. And the maximum COP is for a Carnot refrigerator, and that's equal to, it just depends on the operating temperatures. And in all these formulas, the temperature is in the Kelvin scale. Okay, so that was the summary of this chapter. Entropy and heat engines and refrigerators is what we did. All right, guys, so we'll stop now. And